Learning target 10B ellipses. So I want to start with the picture that we have down here. So on this picture, this is one example of an ellipse, and we're going to go through the definitions and talk about all of these points. What I want you guys to know right now is the ellipse is the black curve. So it's this outer elongated circle, or this oval-like shape that we have is our ellipse. So all the points that are on this black curve out here are the points that actually make up the ellipse. All these lines in between that we have, so the green lines here, the blue lines, and the purple lines, those are going to be part of my definition, which I'll come back to. But an ellipse itself looks like this outer black elongated circle curve that we have here. So our formal definition of an ellipse says that an ellipse is the set of all points P in the plane, so all these points out here along this outer curve, all points P in a plane such that the sum of the distances from a point P on the curve to two fixed points F1 and F2 is a constant distance K. Now those 2 points F1 and F2 are called the foci of an ellipse. So on my graph, F1 is over here on the left side and F2 is over here on the right side. Each one of these is a focus, and the plural of focus is foci. So I have 2 foci on an ellipse, versus the parabola, which we talked about last time, just has 1 focus on it. But for an ellipse, I have 2 foci. Now what this definition is talking about with these distances is kind of summarized down here in this statement. So if I look at this blue line here, so it goes from F1 to this point up here in quadrant 1 on the ellipse down to F2. If I add these 2 distances together, that distance is going to be equal to the distance of these 2 green lines added together, from both F1 to this point over here in quadrant 3, all the way back to F2. So if I take the sum of the blue distances, that would equal the sum of the 2 green distances, which is also equal to the sum of these purple distances. So this purple line is running from F1 to the negative y-axis back to F2. So the distance for the purple lines is equal to the distance of the blue lines is equal to the distance of the green lines. And that's equal to this value K, which was from our definition here. So a visual way to think about this is if I were to take a string, so let's imagine that the blue line right here is a piece of string, and it's taped down on the left side at F1, and it's taped down at the right side of F2. So let's pretend that that's taped down on my paper. Now if I take a pencil and I put it where this 2 blue lines are intersecting on the ellipse, then what that tells me, I could take my pencil and kind of drag it along here. When I do that, I would actually end up drawing the entire ellipse out here, and I could curve it down here. It could keep curving along. Since they're taped down at the 2 foci, those 2 ends are not moving, but the string is actually creating my ellipse that I have there. Now I recommend that that's something that you guys actually try on your own paper. So if we were in class right now, I would be doing this on the board. I would be taking a big piece of string or twine, and I'd be taping it down at 2 places that are on the same axis to each other. So I would draw an X and a Y axis, and I'd tape them both down, same distance from the origin on the X axis, and then I could end up drawing this entire ellipse as we draw around there. What I want you guys to see from here is you can kind of see 3 snapshots of it here. So the blue line would be a snapshot of it. As it curves around, it would intersect over here, and I would get the snapshot of the green lines. And if I keep tracing it around, I'd end up getting the snapshot of these 2 purple lines, but it could keep going all the way around from there. What's key here is that the foci is actually what creates the elliptical shape that I get. And the further the foci are apart, the more kind of flattened out and stretched it's going to be. If I take the 2 foci and I move them closer together, I would end up getting a circle. So the reason I get an ellipse here is that instead of having the 2 foci at the same point, the closer I move them together, if they were to land up on top of each other at 0, 0 here at the origin, I would actually end up with a perfect circle there because my foci are now at the same point. So a circle is actually a type of ellipse. It is just the perfect type where the radius is equidistant all the way out. versus in an ellipse, it's where the foci have been pulled further apart from the center. So I do still have a center at 0, 0. The foci have just been pulled apart, which is causing this graph to stretch out. The other two definitions that we have to have down is this major axis and the minor axis. So the major axis is the segment that contains the foci. So the major axis here is the x-axis. It has both F1 and F2 on it, and its endpoints are called the vertices of the ellipse. So the endpoints here on the major axis, which if I do them, I'm going to highlight them in yellow for us. So I have these two endpoints right there, and I have another endpoint over right there. Those would be called the vertices of my ellipse. Now, on the minor axis, which is the axis that runs perpendicular to the major axis, on those endpoints, we call those covertices, and those I've kind of highlighted in pink for us here. So the points that intersect the ellipse on the minor axis are called our covertices, and the 2 points that intersect our ellipse on our major axis are called our vertices. Now I know that this is a lot of vocab, and we have a lot of different terminology going on here, but we're going to go through quite a few examples to help us get used to this. The big thing I want you guys to remember is that the major axis has the vertices and the foci on it, and the minor axis has the covertices on it. Okay. Before we jump into an example, I want us to look at the two different types kind of side by side here. So we have type 1, which is a horizontal ellipse, and type 2, which is a vertical one. So the horizontal ellipse is actually similar to the same graph that we saw up above. The major axis here is a horizontal line, which is hence the name horizontal ellipse, and the minor axis is the vertical line. Now for this guy, the equation for this standard horizontal ellipse, I'm going to write out for us, is going to be of the form x squared over a squared plus y squared over b squared equals 1. An important thing to keep in mind here is that this is true only if a is bigger than b, and both of those numbers are going to end up being positive. The other thing that I want us to fill in right away is our major axis here is a horizontal line, so we'll have to keep that in mind. Now the vertices are actually already labeled on my graph. They're these two endpoints that are in blue that we have here. Now because they're a horizontal ellipse, it's on the x-axis, so my vertices here are going to be some number, comma, 0 that we get there. Now the number that it's going to be is actually based off of that equation. So our vertices up here are actually at the values a and negative a. So I can write this as plus or minus a comma 0 because I have that one at a comma 0 and my other side at negative a comma 0. And that a is the same value that we're actually taking and squaring and dividing x by. Now our covertices are on our graph already. They're the green dots on the y-axis. Now since they're on the y-axis, they're going to be y-intercepts, so they're at 0, comma, plus or minus a number, and the number that they're at is actually b, and that is also coming from our equation that we get up here. So this one on top there is at 0, comma b, and this one down here is 0, negative b. Now my foci are also labeled on my graph. They're these red points right here, and they're on the x-axis as well. So their x-intercepts, or their coordinate pairs, which are x-intercepts, are at plus or minus c, comma 0. Now this c, we need a way to relate that back to a and b. So c, no matter which type I actually have, I can relate it back using this equation, which is c squared is going to be equal to a squared minus b squared. So now I know that's really close to the Pythagorean theorem, but it is c squared equals a squared minus b squared, where a and b are the values that are coming out of our equation, which are our vertices and our covertices, and then our foci I get through this equation on here. Now on our vertical ellipse, I pretty much have the exact same thing, I just flip-flop a lot. So now instead of my major axis being on a horizontal line, my major axis is now a vertical line. What that ends up causing then is my equation looks similar, so I still get x squared over something plus y squared over something equals 1. The difference here is because it's a vertical line, since a is always bigger than b, my a squared is now going to divide my y, since the y is the bigger value, and my smaller value, which is b squared, is now going to divide the x squared. So if I go to fill out the rest of these, I still have vertices that deal with the a value, but they are now at 0, comma plus or minus a, because they're on my y-axis. So there's 0, comma a, and then over here we have 0, comma negative a. Likewise, my co-vertices are still involving the b value, but they're at plus or minus b, comma 0, because they're on the x-axis. So this guy is at b, comma 0. Oops, let's grab the eraser real quick. So that guy is at b, comma 0, and the left side is going to be at negative b, comma 0. And again, those are x-intercepts now because I flipped my ellipse. So my co-vertices are now on my horizontal axis. And my foci, I get the exact same way I did before. So I use this equation down here, c squared equals a squared minus b squared. But again, they're going to flip-flop, and I now get 0, comma plus or minus c, since they're on the y-axis. So that top guy is at 0, comma c, and this guy down here would be at 0, negative c. Now, of course, all of this is only true because we're leaving our ellipses centered at the origin, which we are going to do for all problems in this section, and that we are going to look at in this unit. So I want to point out some similarities that they both have. So in both cases, I have this fact to be true, that a is bigger than b is bigger than 0. So that is true for either case. If you notice in the equation, the only thing that flip-flopped is where did the a squared and the b squared go. So for each of these, the a squared, since it's the bigger number, is always going to divide the variable that it is stretching further in. So in this case, because I'm stretching more along the x-axis, I'm dividing x squared by a squared. And on the flip side over here, because I'm stretching along the y-axis, my y squared is now divided by a squared, which is what causes my left side to be horizontal and my right side to be a vertical ellipse. And on each one of these, the vertices are always at a, so either the x-intercept or the y-intercept. The co-vertices are always at b, either being a y-intercept or an x-intercept. And the foci is at this c value. Whoops. The foci is at this c value that we get, which is coming from this equation down here. And this equation, c squared equals a squared minus b squared, works for either type of ellipse that we have. This is going to be some stuff that you're going to want to have memorized kind of off the top of your head. The biggest things to keep in mind is that whichever variable we're stretching by, that's the variable that gets to be divided by the a squared, since it's the bigger of the two terms. Okay, let's look at our first example. So in this first example that we have here, what we're going to end up doing is, given the equation, I want us to find the vertices, the co-vertices, the foci, and we're going to graph it. But we're going to first start by stating what type of ellipse this is. So when I go to my equation, I've got x squared over 16 plus y squared over 4 equals 1. So it is in this standard form. What I'm noticing is the fact that this piece right here with the x squared has the bigger of the two numbers on bottom. So 16 is greater than 4. So what that tells me is that this is going to be a horizontal ellipse, because the bigger number is with the x variable. So this will be stretching horizontally. What that tells me then is that a squared must be 16. So I can solve this for a, and I get a to be plus or minus 4. I also know that my b squared value is coming from the other part of my equation, so the 4 right here, which means that b squared is going to, or b, not b squared, we already had b squared. that means that b is going to be equal to plus or minus 2 when I take the square root there to get rid of the square. This then gives me my vertices, so this is going to create my vertices with the plus or minus 4 for A, and the plus or minus 2 for B is going to create my co-vertices. Since it's horizontal, that means that my vertices should be x-intercepts. So my vertices over here then are going to be at plus or minus 4. Are going to be at plus or minus 4, comma 0, because they're x-intercepts, which I'm going to go ahead and plot right now. So we're at 4, 0 right there, and negative 4, 0 on the left side. My co-vertices are dealing with this b value, and they have to be on the opposite, so they're y-intercepts, which means these guys are at 0, comma plus or minus 2, which I can go ahead and plot up at 0, 2, and 0, negative 2. The last thing I have to figure out is what are my foci. So to figure out my foci, we're going to use that equation involving c squared. So c squared is equal to a squared minus b squared, and I can sub this stuff in. I know that a squared is 16 and b squared is 4. So if I subtract those two, I get c squared is going to be equal to 12. So square rooting both sides, I get c equals plus or minus the square root of 12. But the key thing here is that I can continue to simplify this. So I do have a perfect square of 4 inside, so I end up getting plus or minus 2 root 3. These values are going to be my foci, and because my foci is always with my vertices, they're going to be x-intercepts. So my foci then, I could plot them. I'm not going to plot them exactly since 2 root 3 is an irrational number. But before I plot them, I'm going to go ahead and graph the rest of this. So all I need to actually graph my ellipse is to have my vertices, which I plotted on there, and then my co-vertices. And now from here, I'm going to sketch it just like we did the circle. So it's going to be more of this oblong shape as I curve that guy around. And then let's fill in our foci up here, which are at plus or minus 2 root 3, comma 0. Okay, and that is our first example. The biggest thing to keep in mind here is when I'm given this equation for an ellipse, I'm paying attention to which one, the x squared or the y squared, has the bigger of the two numbers that I'm dividing by. Now, because 16 is larger than the 4 and 16 is with the x, that tells me that I have a horizontal ellipse, which is what then told me that my vertices are x-intercepts, and so are my foci, and then my co-vertices are on the minor axis, so they are my y-intercepts then. Okay, why don't you guys try the next example down below? Okay, let's check example B. So the first thing I'm looking at is which of these two is bigger. So 64 is going to be a bigger value here, and because 64 is with my y squared, that means my type of ellipse is this time is going to actually be a vertical ellipse. Now, because 64 is my larger value, it's my a squared. So that tells me that a is going to be plus or minus 8. 25 is my smaller value, so that means that 25 is equal to the b squared value. So b is going to be equal to plus or minus 5. Now, regardless of which type of ellipse it is, I know that my a is always my vertices. Excuse me, a little typo there. But my a is always my vertices. And my b is always going with my co-vertices. Because this is a vertical ellipse, that means that my vertices are now y-intercepts. So I can write my vertices then as 0, comma plus or minus 8. And I'm going to go ahead and plot those. So I'm at 0 all the way up at 8 and 0, comma negative 8. My co-vertices go with the b values, and since these are on the minor axis, they're going to be x-intercepts. So they're at plus or minus 5, comma 0. So here I am at 5, 0, and negative 5, 0. Now again, this is enough to get the entire graph, so let's go ahead and sketch it, and we're going to get this oblong shape that we're getting. Not as nice and pretty as the last one, but the best I can do there. And this does kind of curve out through it. The foci are the last thing to get, so we're going to go back to that c squared equation. So remember, c squared equals a squared minus b squared. So when we're solving this guy then, I know that my a squared is 64 and my b squared is 25. And when I subtract those two then, I get c squared to equal 39. Now again, I'm going to square root both sides, so I get c to be plus or minus the square root of 39. Now, unlike before, 39 does not have any perfect squares in it, so I can't simplify it, and those are going to be the values for my foci. Because this is a vertical ellipse, my foci is also going to be on the y-axis, so they will be y-intercepts, and those guys will be 0, comma, plus or minus the square root of 39. Okay, we've got one more graphing example that I want you guys to try first. So why don't you guys try example C real quick? Okay, so example C is a little different. This is actually not in standard form. The reason it's not in standard form is because of this 225 over here. So if I scroll back up and I look at the standard forms for both of these, I'll notice that they were both equal to 1. Yes, they both had fractions, but they're more importantly, both of them are equal to 1, and that's what I need to pay attention to. So I need to create this so that I can get it into standard form so that I can get this guy equal to 1. So let's write out our equation on the side. We have 25x squared plus 9y squared equals 225. And now because I want this to be equal to 1, I'm going to end up dividing through by 225. And because I'm going to divide through it on the right side, I'm also going to divide through everything on the left side. So the x squared piece and the y squared piece. Now on the right side, that's going to be nice and equal to 1. On the left side, I need to reduce these fractions. So 25 over 225 is actually equal to 1 over 9. So I get x squared over 9. The reason being is because 25 goes into 225 9 times. And on the other guy, I end up getting y squared over 25 because 9 goes into 225 25 times. This then will be my standard form. Now that I'm in standard form, I'm going to pay attention to which of the two terms are going to have the bigger denominator. So in this case, the y value does, which means that this is going to be a vertical ellipse. I also know then right away that my a squared is 25 and my b squared is going to be equal to 9 from my two denominators. Just like before, I'm going to square root both of these, so I get a to be plus or minus 5 and b to be plus or minus 3. The next thing I want to pay attention to is which axis are these on? Well, because I have a vertical ellipse, then that means that my vertices, which are the a values that I'm getting, are going to be y-intercepts. So they are going to be at 0, comma, plus or minus 5. So I can go ahead and graph those. So I'm up here at 0, 5, down here at 0, negative 5. The next thing that I have on here is my b value are my co-vertices. And because these are always on the opposite guy, these must be x-intercepts. So my co-vertices then will be at plus or minus 3, comma, 0. So I'm at 3, 0 and negative 3, 0. Again, this is enough to get the shape of my ellipse. So if I start up here, this guy is curving down, coming all the way down and back around. The last piece we do have to find is our foci. So our foci, to get those, it's my c value. So we're going to use c squared equals a squared minus b squared. So subbing in, I know that I have 25 minus 9. So c squared is going to be equal to 16. Now when I square root that guy, I end up getting c to be plus or minus 4, since 16 is a perfect square. These guys are my foci, and what that tells me then is that because my vertices are y-intercepts, because this is a vertical ellipse, the vertices and the foci are both going to be y-intercepts. So I'll write these up here, and they're going to be at 0, plus or minus 4. Now in an example like this, because my foci appeared at integer values, I'm going to go ahead and graph them so we can see where they would fall on our ellipse that we have. So I have one up here at 0, 4, and one down here at 0, negative 4 that we're getting. Now I'm not going to ask that you guys graph the foci unless they appear at integer values, just so that we can get the exact graph that we have. Okay, let's look at the next type of equation. We're going to do kind of the exact opposite. So we're not going to worry about graphing them. What we are going to worry about is getting the standard form of this elliptical equation that we have, given some pieces of information. Now, I don't have to give, or a problem doesn't have to give you as the vertices, the covertices, and the focus. I actually just need 2 out of those 3. And the reason I need 2 out of those 3 is because we're going to use this equation a lot. We've already used it in every example, and we're going to continue to use it. This is the equation that relates our vertices, our covertices, and our foci together. And by using this, as long as I have 2 of those pieces of information, I can always find the third. So let's look at our first example. It says, what is the equation of the ellipse in standard form? So I want it to be equal to 1, centered at the origin, with a focus at -5, 0, and a covertex at 0, the square root of 39. The first thing I'm going to focus in on is actually the focus. So remember, the focus is always on our major axis, and so because the focus is an x-intercept here, this tells me right off the bat that I actually have a horizontal ellipse that I'm going to look at. The reason that I know that it is going to be a horizontal ellipse is because my focus is an x-intercept here, being at -5, 0. So that tells me that my general form for this will be x squared over a squared plus y squared over b squared equals 1. The reason the a squared is with the x is, again, because it is a horizontal ellipse, since my focus is an x-intercept. The other thing this tells me is that I know what c is. C is equal to -5. Technically it's plus or minus 5, since I do have 1 on each side, but more importantly, that tells me that c squared is going to be equal to 25 if I square both sides. Now, that's not going to help me fill in a squared or b squared yet, but I'm going to come back to this to help us in a little bit. Now, the next thing let's focus in on is what the covertex is. So because the covertex is at 0, the square root of 39, that tells me my b value. So that means that b is the square root of 39. So b squared then, if I square both sides, I just get 39 by itself. Well, if I'm starting to fill out my answer, I can do that already then, because I will have x squared over something, which we'll have to find, plus y squared over 39 equals 1. The last thing I have to figure out is, what is this missing a squared? Well, I have c squared because they gave me my focus, and I have b squared because I have my covertex. So I'm going to go back and use this equation and actually solve for a squared. So our general equation says c squared equals a squared minus b squared. C squared is going to be 25. We're looking for a squared, and b squared is going to be 39. So to get a squared by itself here, I want to add the 39 over, and when I add the 39 over, I get 64 is equal to my a squared. Now I could square root both sides and solve for a, but I'm actually just after the equation, so all I need is the a squared, which means I'm going to plug in 64 there, and that guy will then be our final answer for our equation in standard form. Now the key things that we have to pay attention to is this information. So I'm given the focus and the covertex. The reason I chose the focus to look at first is because the focus, or the vertex, but in this case I don't have my vertex, so the focus is always going to be on the major axis. So I want to pay attention to, is the focus an x-intercept or is it a y-intercept? Now in this case, because the focus is an x-intercept, that tells me right away that I have a horizontal ellipse, which means that I'm looking at the equation where the a squared is attached to the x squared piece since it is horizontal. From there, I can figure out what c squared is by squaring my focus. I can also figure out what b squared is by squaring the covertex. Lastly, I use that relating equation that relates a, b, and c, and I can solve for a squared and then substitute that in as well. Okay, let's look at our next example of this type. I want you guys to pause the video right now and try example 3 on your own. Okay, so example 3 is similar to the last one. I have a focus again, and I have a covertex. What makes this a little different is, well, I have different numbers, but more importantly, my focus this time is no longer an x-intercept. It's actually a y-intercept, which tells me that I have a vertical ellipse that I'm looking at. The most important part of that being a vertical ellipse tells me that I'm looking at the equation x squared over b squared now, plus y squared over a squared equals 1. The reason they flip-flopped is that a squared has to go with the type of ellipse it is, and since it's vertical, the a squared has to go with the y value. The other thing I know from the focus is that c is 7, so c squared then is going to be 49. Using my covertex, I know that b is equal to -4, really plus or minus 4, but I just need one of them. So squaring both sides, I get b squared is equal to 16. That I could fill in right away, but the last piece I'm missing is this a squared value. So we're going to go back to that equation we keep using over and over again, that c squared equals a squared minus b squared. So subbing them in, 49 is going to be equal to a squared minus 16. Again, if I add that guy over, I get 65 is equal to a squared. So I can use all this information and sub to get in my final equation. So we get x squared over 16 plus y squared over 65 is equal to 1. And that right there will be my final equation for the standard form of this guy. Okay, let's look at example 4. So example 4 here, they're saying the same thing. We want an equation of the ellipse in standard form, centered at the origin, but this time they gave us a vertex and a covertex. So using that information right now, I want you guys to pause the video and decide which type of ellipse we have. Is it horizontal or is it a vertical ellipse? Okay, let's check that now. So since we have a vertex here at 6, 0, that vertex is actually an x-intercept. And my vertex and my focus always appear on my major axis. So that tells me that since my vertex is an x-intercept, that my major axis is a horizontal line. So I have a horizontal ellipse then. So this guy is going back to that form, x squared over a squared plus y squared over b squared is equal to 1. Because being a horizontal one, I want my bigger of the two numbers, which is the a squared, to be with the x. That also tells me right off the bat that my a is equal to 6, because they gave me the vertex this time, which is always the a value. So squaring it, I get a squared to be 36. Now the other piece of information they gave me was a covertex again. So that's my b value. So I have b to equal -3. So b squared then is 9. Now in this example, I have everything that I need right off the bat. I can start filling in that equation, and I get x squared over 36 plus y squared over 9 equals 1. There was actually no need to go ahead and find the foci since they gave us the vertex and the covertex. So we had all of that piece of information already. Okay, our last example down here, example 5. I want you guys to pause the video again and try this one on your own. Okay, let's check example 5. It says, what is the equation of the ellipse in standard form, centered at the origin with a vertex at 0, -10, and a focus at 0, 6. So this time they gave us the vertex and the focus. Now both of these always appear on the major axis, and since both of these are y-intercepts in this case, then I have a vertical ellipse. Which means that I'm looking at the equation x squared over b squared plus y squared over a squared equals 1. Because it's vertical, I want my a squared to go with the y value. I also know that since my vertex is at -10, that my a value is -10. So my a squared is 100. And because my focus is at 6, my c value then is 6, and my c squared is 36. So I can go ahead and fill in part of this equation. I can fill in the a squared value, but I still need the b squared. So going back to our trusty equation, c squared equals a squared minus b squared. I know that 36 is going to be equal to 100 minus b squared. Well, now I'm trying to isolate b squared. So if I add it to the other side, I get 36 plus b squared equals 100. And to get b squared by itself, I'm going to subtract 36 to the other side, and I get that b squared is going to be equal to 64. That is all I needed to fill out the rest of my equation. So I get x squared over 64 plus y squared over 100 is going to be equal to 1. And that right there will be our final equation that we have. Now remember, on all of these, the key important facts that we want to take away is that our vertex and our foci are always on our major axis, which determine which type of ellipse we have, and our co-vertices are always on our minor axis. In the equations, if I have a horizontal ellipse, then the a squared is with the x, and if I have a vertical ellipse, the a squared is with the y, since the bigger number goes with the variable that we are kind of stretching by for each of these ellipses that we're looking at. Okay, that is the end of Learning Target 10B.